Okay, so before we start, do you have any question on the videos of the introduction? Is anything not clear so we can go over your questions before we start? Okay, so today I will introduce for you chapter 2 and assign for you some videos to watch. So next time we start to do practice together, we do problems on chapter 2. So the main idea until now is that in this chapter, we have seen that in this course, we have seen that energy can be present in several forms. And the purpose of this course is to understand how we can convert it from a certain form to the other. Okay? Now, energy can be present in several forms. For example, we can have electrical energy, we can have chemical energy. And also in thermodynamics, we see that energy can be transferred in form of heat. So one very important form of energy is heat. And we can see how, let's say, several bodies can exchange energy by heat. And we have 3 modes of heat transfer, and we'll focus on the modes of heat transfer in the following chapter. Do you know what are the main modes of heat transfer? What are the modes of heat transfer? We can divide them mainly into 3 types. The first one is conduction. The second one is convection. And the third is radiation. So the purpose of this chapter will be to understand the physics first of these different heat transfer modes, and to go over several engineering applications to see how we can find the energy balance equations and how we can find the variation of temperature when we have transfer of heat through these different modes. I will start first by conduction. So mainly conduction will take place when you have a variation in temperature. Okay, conduction can take place between different bodies or in the same body. Okay, so for example, if you have 2 objects, A and B, and these 2 objects are in contact with each other, in case you have variation in temperature between these 2, so if TA is different than TB and the 2 objects are in contact, you will have like a transition period where the temperature of both bodies will change until reaching equal temperatures. So let's say TA is larger than TB. Due to contact, heat transfer will take place from highest temperature to lowest temperature. So with time, TA will be reduced and TB will increase until reaching equilibrium when the 2 will be at constant temperatures. So this is thermodynamics. Thermodynamics will deal with, if you want, the transient processes to go from one equilibrium state to another. Now, you can have conduction in the same fluid, the same solid. So no need to have 2 different objects. If you have, let's say, same solid, and that if you heat, for example, this part here, due to heating of this zone, what will happen is that at the micro scale, if you go to the micro scale, you will have like vibration of these particles. And because of these vibrations, energy will be transferred from these particles to adjacent particles. And this is how by conduction you can have heat transfer from this side, which is heated, and where you have higher motion of particles, to particles at the end which are at a cooler temperature. So this way, by vibration and collision between adjacent particles, you can have heat transferred from one side to the other. Conduction is also present in fluids and in gases, but it's more dominant in solids. Why? Because in general, we have high conductivity property for solids. And the conductivity property is the one that will be used to calculate the conduction flux. Okay, so to start with, a simple formula that can be used in 1D conduction. What do we mean by 1D conduction? In general, you can have conduction in all directions. So conduction can be in three directions in case you have a 3D applications. However, in the majority of our applications, especially let's say in the design of buildings, whenever you have an envelope, you have an envelope of several layers of the of your building, and this envelope will separate the inner space from the outer space. So here we have, let's say, the outer space. Here we have the inner space. And we have a difference in temperature between these two sides. We know that, let's say, this is Tn and this is Tout. What will make a difference between these two is the level of insulation in the envelope. Okay, so in general, you want to have high insulation of your envelope to reduce heat transfer between the inner and the outer space. And this will be affected by the material you select. What are the properties of these materials? What is the conductivity? What is the thickness of the layer? Okay, and we'll see in general that if you have a wall of a certain thickness, you know that the dimensions in height and length are much larger than the thickness. This is why heat is easily, if you want, conducted through this dimension, because you don't have a large distance for the flux to go over. So the smaller the distance to go over, the lower will be the resistance to heat. This is why in buildings, since the thickness is small compared to other dimensions, plus the main temperature difference is between the inner and outer sides of the thickness, conduction will mainly be in this direction, and it will be dominant over conduction in other directions. So we can treat conduction in a building's envelope as 1D conduction. And we can show that for 1D conduction, the conduction flux Q second, which is in watt per meter square, is calculated as minus K times the area times dt by dx. And if you want to, sorry, without A, okay? If we multiply by A, then we don't get Q second, we get Q, because Q second is defined per unit area. If you just want, and this is called flux of conduction. So this is the heat flux of conduction. Now, if you multiply by A, okay, then you get Q conduction. Q conduction in watts, which is equal to minus Ka times dt by dx. Okay. So in this case, we can see that higher the conductivity is, higher will be the flow rate from between the inner and outer space. So for example, in the building envelope, we tend to select materials with small conductivity in order to not have heat losses through the envelope. Plus, of course, higher is the exposed area. So if you higher the area of walls, higher will be the heat exchange. And on the other hand, concerning the thickness, we can show that in 1D systems, the variation of temperature by conduction is linear. So we can replace if you want, minus dt by dx by the variation in temperature delta T over the length. And just let me comment on the negative sign here. When you take x in this direction, okay, the flux to be in positive x, you should have T out larger than Tn. So always, if you want, the flux direction is opposite to the gradient of temperature, because when T out is larger than Tn, this means that dt by dx will be negative. Okay, and that's why we put the minus sign, because heat flux by conduction will always tend to go from highest temperature to lowest temperature. Okay, so from here we can say that the conductive flux is proportional to delta T, which is the difference in temperature between the two sides, and inversely proportional to the thickness here, which is L. And we'll see in this chapter how to deal with multi-layer envelope. So what can we do if we have several layers? So we have different materials with different conductivity. So this is in brief the first mode of conduction, of heat transfer, which is conduction. Now, the second mode of heat transfer that we will focus on is convection. Whenever we have convection, we have interaction between a surface and a fluid. And in general, the fluid is in motion. So the fluid will be moving. Now, it can move with small velocity or it can move with high velocity. And depending on the velocity, we can define if it's a natural convection or if it's forced convection. So if you have, for example, a room and just you have air moving close to the surface at relatively small velocity, this is natural convection. However, if you have a fan that is blowing air on the surface, then you have forced convection. And in this case, for example, let's say you have the surface at a temperature Ts and the fluid is moving at a temperature T infinity. What will happen is that, let's say T surface is larger than T infinity, then the fluid motion will transport with it heat from the surface. And since the surface in general is a solid surface, then we say that convection is combination of conduction and fluid motion. Why we say this? Because within the solid, heat is transferred by conduction. So at the surface level, when you consider the surface as a part of a solid, you have the flux getting out of the solid as a conductive flux. And this conductive flux will be transported by the fluid in the form of a convected flux. So we say then that Q conducted at the surface level, and this conductive flux can be written as minus K of the solid times the area times del T, if you want this direction Y, so it's minus del T by del Y at the surface level. So this is the gradient of temperature within the solid, will be equal to, the convected flux. Okay, the convected flux from the surface towards the fluid is equal to H times A times delta T. Okay, so the convected flux can be expressed function of what we call a convective coefficient, and this convective coefficient is defined empirically. So we do experiments to be able to assess H. In this chapter, we'll develop some empirical relations together and see how we can find H from experiments. Now, the third mode of heat transfer is heat transfer by radiation. And whenever we say radiation, we don't have the main difference with other mode of transfers is that we don't need a medium to have heat transfer by radiation, in opposition to conduction and convection. For conduction to happen, you need collision between molecules. For convection to happen, you need interaction between a solid and a fluid. However, for radiation to happen, you don't have to have a medium. And you can just have an empty space. The only condition is to have surfaces at different temperatures. So you need two surfaces, surface 1, surface 2. Of course, you can have a medium between them, but if you don't have, it's not a problem. So if you have air between the two surfaces, or you have water, or you have vacuum, in all cases, you can have radiation. Why? Because the main mode of heat transfer by radiation is through electromagnetic waves. So this will take place through electromagnetic waves, and the propagation of electromagnetic waves does not require to have a medium to be transferred from one surface to the other. So this is why we say that radiation mode does not require a medium. It just takes place through exchange of electromagnetic waves.